Recently, I was talking to someone who said there were some new AT-Tiny microcontrollers out in the wild and that I should try them. So I ordered some, and in this video, I'm going to make a programming rig, try programming them, and then show you how I get started with the new microcontroller. We'll see what we can do with the peripherals. I probably won't cover everything, but I'll try to at least get a good start, and we'll see how it works out. So join me as I stumble my way through learning a new microcontroller.
Here's the dev board that I made. I've got it plugged into the Atmel ICE programmer. I wired up a UDPI adapter, so we should be able to program it with just one wire. I do think we have to select between that being a GPIO or reset or a UDPI, but it should be all right. So let's see if we can get this set up in Atmel Studio 7.
Here we are at Atmel Studio. Let's go to Tools, Device Programming. Our tool is the Atmel ICE. The device is the AT-Tiny 212. Interface, UPDI. We have no choice there. Let's apply that. Kaboom, all right. And we're going to read the device signature. There we go. We have life. Yay. What does this do? 128 bytes of EEPROM. Ooh, and user signature. I'm not even sure. What is that? Fuses. This is important. This is what the values look like in memory, but then they have like the human readable versions up here. There's one thing to note. I'm pretty sure this has a default of a 6x divider for the clock. So just cold turkey, it'll actually run at about 3.3 megahertz. So we'll have to change the change protection register in the code and actually speed that up when we start, because of course we want all the megahertz. Oh yeah, and then the reset, it's either GPIO, UPDI, which is what we're using right now, or reset. And we don't want to change that, because if we do, we'd have to use a 12-volt programmer, which means that I have to rig up another 12-volt programmer to fix it. And I don't know how to do that with this chip. So just as it is, it should be ready to program. Here's the data sheet for the AT-Tiny 212/412. Now this is going to be in the same price range as the older 25, 45, 85. However, compared to those, it has a lot more features. It's still a 5-volt device. You can run it at a lower voltage, but you won't get the maximum speed out of it. The old series, they just had a universal serial interface, which is cool, but it wasn't really appropriate for some things like UARTs, because it was only 8-bit, which means you don't get the start bit. So I guess the first thing we should try to do is blink an LED. So let's go down to port in the data sheet. Let's just skip to register descriptions. All right, let's just skip to the register summary. Dir set, clear, toggle, out, set. Oh yeah, so what this one can do, it can actually atomically change a pin on a port. My amazing, exciting life. Okay, let's call this AT-Tiny, AT-Tiny 212 test 2. I already did a few tests with this, of course, off camera to make myself look smarter. All right, gonna do an executable. And let's give me the Tiny family and the 212. All right, so yeah, we have little 2K flash, 128 bytes, 64 bytes of EEPROM. Sounds good. Let's get this project out onto a tray. Nice. Do my indents. Apparently some people hate that, so, well, I don't care. Port A, so let's see, DIRA A. Let's go back to the data sheet. Okay, I'm going to have my scope hooked up to PA7, so that'd be the high bit. So that would be DIRA A, and let's set, oh, how my cursor get over there? 0B, 1, 1, 2, 3, 1, 2, 3, 4. And then let's just do a toggle. Port A equals, oh, here, I'll do it in hex just to make people even more upset. It went from binary to hex? What a loot. Oh, how about binary to hex to decimal? No! No, Ben's a monster! Uh-oh, DIRA undeclared? Incompatible type? Oh, it must be using some other kind of structure. Let me try. I think it's port. Oh, there we go. Port A. Okay, so we can either do port A period dir. Oh, I see. Okay, so it's telling us what to do. So we could either declare it like this, or we could go point A period, which means we're accessing a structure of some kind. Who knows where it is? Okay, all right. Oh, and then this would be out, I believe. Port A dot. Okay, what's our choices? Out. Great. Equals 81. Wait, why did I make it 81? That's dumb. Port A out equals 0. Okay, will that build? Okay, cool. Let's try it out.
Looks like we have a sign of life. So this scope was sent to me by Daniel, an associate of Keysight. And thank you very much, Daniel. I noticed Dave Jones has one of these as well. This is a DSO X1204G. It's a 200 megahertz scope. It's actually physically the same size and basically the same format as the 70 megahertz scope I've used before. It's a good desktop scope. It's kind of physically small. Yeah, and also there's an event coming that Keysight has. So I'll have links for that in the description below. I just told them, I'm like, yeah, I'll probably make some videos. Like, you know, I'm always using scope, so it shouldn't be very hard to get it in there. All right, let's stop this, take a look. I'm going to go to measurements. I'm going to add frequency. All right, 558 kilohertz. All right. Now remember, we didn't do the initial clock divider yet, or we didn't disable the clock divider. So keep that in mind. Now again, remember we're going high, low, high, low. So as far as the code's concerned, we've got one instruction to go high, one instruction to go low, and then a loop for the while statement, which adds, it adds time. Then we go back to that. But we can also talk about like the atomic settings as well. So let's get rid of the clock divider first.
Guessing we're going to have to do the change protection register. So it should be CCP. Oh, well, this is a different thing, but so this, yeah, as I mentioned before, this is allegedly an AVR core with PIC peripherals, which makes sense because Microchip bought them. Please, Microchip, but for the love of God, do not get rid of Atmel Studio. It is so much better than MPLab X, which I also have installed. Anyway, yeah, so you can see you can actually configure some of the pins differently, which is that's a very modern feature, but for a little tiny chip like this, it's actually pretty cool. Well, here, let's just search for it. CCP. Configuration change protection. Okay. Oh, there's the link. All right. Okay, so let's register CCP. And I don't think there's a structure to it, so we can just type in CCP. And we want to unprotect protected I/O registers, so we're going to tell it D8. CCP equals hex D8. Great. Now we need to change the register that we want to change. And that's going to be, oh, there's configurable custom logic. That's pretty cool. Like you can have chips act as gates, basically. You set up truth tables. Yeah, like Atmel's ARM chips. You don't really see that until you get up to the M4s. Clock controller. Oh yeah, prescaler with 1 to 64 division. Okay, that's what we're gonna want to change. Can we just jump to the register summary? Blah 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 blah. Okay, I'm gonna guess it's this one. Clock select. Oh no, that's which clock we're using. Okay, and the default is the internal oscillator. Prescale division, here we go. M clock control B, P division, 4 bits. And the default is, let's see, 1004. So that would be the 8. Okay, so yeah, that would be a division of 6. So we want a division of 0. Pen, what is pen? Prescaler enable. Well, we don't want to use a prescaler. So basically, we want to hit this register with a 0 because it defaults with a 1 set there, all right? So we're going to just do that and set it to 0. All right, let's resend the code. Oh, no. Oh, does that? Oh, shoot. That's the thing. Remember, the data sheet is kind of language agnostic, right? So knowing that we have to, set, clock control, and then part of that structure is, that's not necessarily always evident in the data sheets. Although this does remind me of, it's more like an ARM than an AVR. Let's give that a shot. Okay, and now you can see we are now at 3.3 megahertz. Again, you have to take into account, it's only getting the frequency of the high, so it's actually twice that. So it's like, what, 6.6? And then that takes into account the jump. So yeah, that makes sense for about 20 megahertz. One cool thing about this chip is it actually has a DAC, digital analog converter, which is not very common for a chip this small and cheap. Looks like that only works on one pin, PA6. So I'm going to hook that up to channel 2 of the oscilloscope. Well, actually, one thing first. We'll have to set that pin as an output for the DAC to work. Okay, so we got that there. Oh yeah, I was talking to people on Twitter about that. Initializations versus acronyms. I didn't realize there was a difference. An initialization is where you say like DOT, Most people don't say, oh, I'm going to get my license renewed at the dot. You would say, I'm going to use the scuba gear. You wouldn't say SCUBA. 8-bit resolution, so 0 to 255. 350,000 kilosamples per second. That's pretty cool. So that would actually work easily for audio. You probably could use this to make a analog video signal, although you'd be limited in resolution because at that speed or lack thereof, you're probably going to hit some bottlenecks. So the VREF is cool because we can actually change it. It doesn't have to be 0 to VCC. It could be something else. Like if we were trying to use like audio or video, we could actually use the 1.1 volt DAC, which is also good because then you have a finer voltage resolution as the maximum voltage or VREF is lowered. Right, so you have 255 divisions of 0 to 1.1 instead of 0 to 5. Okay, blah, blah, blah. Then there's all this. Got you suckers. Register summary. Oh, this is simple. Oh, yeah, here's another thing. We can kind of see the structure. See how this has Control A? Well, all sorts of peripherals on this have Control A. This is definitely where you have to, specify which Control A you're using. All right, so output buffer enable. Okay, that we need that and set it to a pin. Then we also need to enable it. So let's grab this. And there was a gotcha that I found. It's not the DAC structure, it's DAC 0 as the structure. And then Control A, and then, okay, so what would that be in hex? 4-1? Or 1, 1, 2, 1, 2, 3, 4. Just like that. All right, that will enable the DAC, and then I think all we need to do is put data into it, I think. So that would be DAC 0, well, I guess, again, we could type it two different ways. DAC 0 data equals, let's make it a variable. Let's use A++. Instead of C++, it's A++. And that's going to be an unsigned 8-bit. That way it'll just roll over Beethoven. Oh no, DAC undeclared. Oh, see, DAC 0. I guess that makes sense. Because, oh no! Oh, wow! Look at that. Are you a master programmer or a master butcher? Yeah, looks like it's not quite what we want. Here, there's our pin toggle. Let's grab channel 2. One thing that's a little different with this scope, you have 4 inputs, but then you have to push one of these to select what the knobs do, right? So I've got to actually hit I turned it off. I got to hit number 2, then I can adjust number 2. Looks like we're missing something because we should see like a sawtooth on that.
Oh wait, I think we have it. The scope just wasn't set up correctly. Let's see if we can grab this. There it is. Nice. So I have this at 1 volt per division. So yeah, you can see we are getting 1.1 volts.
Let's go from 0 to 128, then back down to 0. I'm expecting we'll see half that, so probably 300 nanosecond delay. Camera started, reprogramming. Makes sense because we're at 500 millivolts per division, so we're just above that, which means we're at approximately 550 millivolts because it's 1.1 volts divided by 2. And let's get a little bit more granular. Yep, sure enough, 1, 2, 3 divisions. So yeah, so the time it takes the DAC to achieve its value is dependent on where it is currently. I'm assuming it uses some sort of internal resistor ladder. So that's important because if you were trying to do something really time sensitive with the DAC, you would have to take the rise and fall time into effect, and the rise and fall time would be different based off of how far you're going. However, if we're talking about audio, I guess we probably could rig up like an LM386 amplifier and try it out. Even like CD quality audio is only like 44,100 or 44,100 samples per second. This would be more than fast enough for that, except for obviously we don't have enough data to put through it. But we might be able to, I don't know, we could rig some stuff up because we could create, whatever kind of waveforms we want. I found an online tool. It was basically a wave generator. So I told it to generate a sine wave with a range of 0 to 255 and 256 elements. So I'm going to put that data into a constant int 8. The reason we do that is so that it is in program memory, not RAM, because this would obviously eat all of our RAM. Unlike Arduino, we don't have to do that progmem thing to put things in a program flash. We just have to do constant, right? So the wave. So what we can do down here, just do for int x equals 0, x is less than 256, x plus plus, And then DAC 0 data equals the wave XM, the wave X. All right, let's send that over. Starting camera. I gotta say, this UDPI interface is pretty handy. It's a lot better than that tiny 10 where I was having to flip those switches. Because the thing to think about also with like the, yeah, I mean, if you look at like an AT Tiny 85, you have the same number of pins, but in order to program it, you need serial clock, MISO, MOSI, and reset, right? So you have to make sure that whatever you have, whatever your application is using on those lines will not affect the programmer. But with this guy, yeah, it's each one pin, but it does everything for you. So I suppose if you had this factory programmed, you could just have it be set to be reset all the time. And then again, you could override it with a 12-volt programmer. But look, I still got 5 pins left over, right? And if we go to I/O multiplexing, PA0, what is it doing? Okay, apparently, well, no, it does have multiple functions besides the programmer. An analog input, chip select. That kind of is annoying. The fact that it's hard, the chip select is hard coded to that. See, we can change where MISO MOSI is, but chip select looks like it's static as well as clock. What else do we have? Oh yeah, there should be. Oh, okay. Looks like the 2-wire interface, aka I2C, or a lot of times they won't say I2C because it's like a trademark of Philips. So it'll be like 2-wire. It's like Sam's Choice generic 2-wire interface, but they mean I2C. Oh, looks like we have pins like these W's here. That would be an output from the timers. There's actually 3 timers on this, and they're quite powerful. There's 2 16-bit timers and a 12-bit timer, and they have all sorts of different functions. Again, more common, the kind of functions that are more commonly found in a fancier microcontroller. So this is a pretty cool little chip. That's why I bought it.
I don't know if you could even see it. There's a little bit of futz right there where the loop repeats. Just a tiny little bit. You wouldn't even hear that if this was like being used for audio. And let's face it, you're not using this thing to keep grandma alive. Oh, I must use the most advanced technology to stay alive. I am a grandma. Well, don't worry, grandma. We programmed this in Microsoft Quick Basic. Oh, what? Beep! I'm with the angels now.
Next, I want to try a system timer with interrupt. I'm going to cheat a little bit. I'm going to use Atmel Start, which is a code configurator. It's at start.atmel.com. Create new project. And we've got the AT Tiny 212. Now we can go over here and we can say, oh, what do we want? We can enable everything, although I don't think we can actually have everything. But yeah, you see everything is here. The analog comparator, the ADC, the CRC, the DAC, the digital glue logic. Yeah, all right, so let's do timer. Let's add 1 timer. While we're at it, let's add a UART. Let's start with just the timer. And I threw a UART in there as well. Another difference between this chip and the other, I think I mentioned this, the AT Tiny 25, 45, 85. Those did have like a universal serial interface, but it wasn't really good for UART because it only had 8 bits of data, which means you don't have your start bit or your end bit, which you need for UART. All right, so here's a project, and we could actually also add pins. So we see we've already consumed some pins with our TX and RX. So if we wanted PA1 to be like a digital button, we could actually click on it, call it sloths, say that it's the digital input, and it'll set that up for us as well, which is pretty cool. Depending on the chip, sometimes these configurators create a lot of bloat, but I'm mostly doing this just to cheat, right? So I'm being very open with you. I'm cheating. Oh, speaking of that, clocks. So this has the default of the divide by 6. This is actually where I figured out that it was the default by cheating and going into Atmel Start. So we're just going to disable the prescaler. Not that it matters because we're just going to be copying portions of the code anyway, but I just thought I'd show you that. So now you see the diagram here. We see now the CPU and everything is running at 20 megahertz, right? Including the timer, which is important, right? All right, so we've got our timer A. So let's say that we're going to use the DAC for video. I don't think it's appropriate, but we can still set up an example for that. Okay, so we're going to want a compare. Actually, no, let's do an overflow interrupt and then include the driver ISR. That'll actually just create the interrupt handle for us. Because it's, we've seen that before. you might not know exactly what to call the interrupt, you know, when you do the function for it. All right, so let's see. So we're going to set the period. Okay, now we are going to use the math. 20 million divided by 15,700, so that would be a horizontal sync pulse. Let's see, well, we're rounded up to 1274. Excuse me. One thing that's cool about this chip, oh, sorry, I just ate lunch. The period can be whatever you want. Like a lot of times the period is, it's set to be like 65535, or it's, you know, it's hard coded to like an 8 or 16-bit number, but I can set it to be whatever I want here, right? So we start at 0, we use a system clock, which means it will be running at 20 megahertz. And then on overflow, which means when we go past the period, we're going to trigger an ISR, and that should be enough. All right, well, while we're in here, let's take a look at the USR. Well, yeah, UART. This chip also has support for IR, so it can actually demodulate IR signals, infrared, like remote controls, and run them through the UART. So that's pretty cool. We're not using XDIR, but we could use XDIR, like, so we could actually, this also supports like RS485, which is a differential signaling serial communication chip. All right, yeah, so now that we've got that set, we can go to code. And you can actually export an entire project from the web page here and import it. It will automatically generate a Atmel Studio solution file for you. But in this case, I'm just going to cheat again. Cheat. So we're going to go in here. So here's timer init. Now, as you can see, a lot of it looks like they basically included everything in this wrapper, but most of it's commented out. So the only thing that we're really doing is we're setting up the timer. We're setting up the interrupts and the overflow, and then we're setting the period. And apparently that's all we have to do. Of course, we'll have to enable interrupts. Oops, I missed something rather critical. Enabling the module. Oh, also, we could set it up where pins are changed when something happens. You can see here, okay, this could be PA3 or PA7, but PA7 is used by the UART, so that actually is not an option. So we can't click on it, or we can, but it would disable the UART. Well, it would at least disable the receive on the UART. You can actually set up the UART to be, you know, just one way or the other, like a half duplex. I promise I will never make mistakes. That's funny. Yeah, I'll never make mistakes, right? All right, so let's just grab what we need, which is just this. So I'm just using Atmel Start to help me bootstrap the timer instead of importing the entire project, which has probably more stuff than I really need. So let's take a look at this. So it's separated this into one line. So it's TCA 0 single int control, and it's putting these values into it. But as you can see, it's, well, here, let me just, because remember, C doesn't really care about lines. So really it's doing that. See, it's a big OR. They're ORing a bunch of values together. Oh, their bit shifting is 0 over. That's kind of dumb. Okay, well, anyway, there's the period. You know, before I was doing it, you know, just by these binary expressions. But yeah, all of those binary positions are defined in software, but you have to bit shift them over. So it's kind of weird. So this expression is not, it's not a bit mask. It's a bit position number, right? So if you wanted this to be enabled, you'd say 1 bit shift, whatever this is. Well, I mean, I guess we could look it up. Let's see, refractor, find references. There it is. Okay, yeah, so that's a bit shift of 4. Great. One thing, when you're doing refactor, you have to be careful because it's actually possible to refactor and rename some of these system files. That would be bad. All right, so if we're going to make this an interrupt, we have to enable interrupts, which is that command, or that function, I should say. And we need the interrupt handler, driver ISR. So let's just grab this. Now this ISR, interrupt service routine, isn't doing anything yet. Okay, since we didn't define any function primitives, we have to put this before. The interrupt flag hat, okay, yes. Yeah, some chips will clear the flag automatically. Apparently this one doesn't. So again, RTFM. I'm just gonna make the while loop eternal. You will go to your eternal reward, Aladdin. Oh, also make sure you include AVR interrupt up there. So DAC 0. I have all these calculators, right? 1.1 volt divided by 256 is that many volts per tick. Copy that. So we take 0.3 volts for black level divided by that, which means 70. Okay, so DAC data equals 70. That would be, well, actually, I'm sorry, it equals 0. And then I'm not going to put in the exact numbers right now. I think it's about 4 for a front porch. So that's going to go 0. That would be the front porch. I'm sorry, the back porch sink. And then we'll go 70, which would be NTSC black. And then we'll just leave it there. All right, so in theory, this should create a horizontal sync pulse for NTSC.
Kitten, seriously, I like petted you a couple times this morning. I fed you. What more could you want? It's like the greatest Disney movie of all time. I who bathe you, dress you, feed you, dress you. I who look upon you without fear. Why invite the calumny and consternation? Stay in here, be faithful, and stay in here. That's right, best Disney movie ever, Hunchback of Notre Dame. All right, so there's the 0 pulse. It's a little noisy. And then we're at 200 millivolts per division. So 200 and a half, 300. That's exactly what we need for the black level. I mean, it might seem like, I was like, oh, that could work pretty well. I mean, maybe it could, but I just think the DAC is a little too slow, at least for this purpose. Because remember, like, if you think about it in broadcasting terms, a TV channel is like 6 megahertz of bandwidth.
So, yeah, that was pretty easy to set up. I mean, actually a lot easier than the other microcontroller that I did. One thing that's also cool about this, I know we talked about this, but see how I have it set to debug? So I just hit this, which means start without debugging. But if I hit this, it will start with debugging. So it's a little tiny chip, and it has full debugging over that one wire, which is, again, unprecedented compared to the previous lines. Some of the Atmels have I think it was called like debug wire, where they could debug over the reset line, but I don't believe that was a feature until you get up into like the 18 megas. We can actually use the debugger to illustrate how one command in C is actually usually at least 2 commands in assembly. So we have vref control and then a value. So in what actually happens when it's assembled is we load the value of 1 from flash and we load it into a register on the CPU. Then we store that register into an area of memory or a register. We store the register into a register, which actually changes the value. So what appears as 1 line in C is actually 2 lines in assembly. So that if I jump to the next instruction, okay, so that's the second thing that happens. And then we go down here. There's a big long line. We have a couple things ORed in here, but the assembler will already OR those bits together. So it will just already appear as a value here, right? So the assembler pre-ORs those values since they're static, and then basically just has a number of memory. However, if one of these OR if one of these ORed values included a variable, then it would actually have to process the whole thing. Yeah, so it's pretty cool that this thing has a debugger on it. I'd like to see that 3-cent micro that Dave Jones took apart do that. Winner, winner, chicken dinner. Bob's your uncle. Unbelievable. I've tried exporting a couple projects, an I2C tester and a UART tester, but I've had problems with both of them. So you can actually download the pack and you'll get a zip file, an AT zip file, which will actually create a new project in Atmel Studio. But I'm having trouble getting these to compile. I think they might be a little too big for their britches because I had like an out of memory error. So I think maybe I'll try since UART is simpler, maybe I'll try that at the low level before I move on to I2C. If you use the auto configurator, it'll create all of these ISRs and callbacks for your function. But like with UART, it should be pretty simple, but at least at a base level. Once you initialize it, if you put data into it, it'll spit it out. So again, I'm cheating by looking at Atmel start. Here's what actually initiates the code. And then looks like, well, the ring buffers, we don't need those yet. So I'm just going to do what I did before. I'm going to copy this. This should be enough to at least make it spit out something. Use our example code. Let's paste what we stole. This looks like we're enabling it with a baud rate of 115,200. Then there's all this. Got you, suckers. All right, do we still have delay? Yes, we do. All right, so Let's go put in a delay. Receive data, transmit data. It's weird that it's got a high and low byte. I wonder why that is. UART. Oh, that's weird. The UART doesn't have a number in front of it like the other one did. Oh, wait, no. If you type 0 and then... Oh, no, I don't have a fun. That's weird. Oh, USART 0? Okay. That equals a bit stripe. Let's try building that. Undefined. Oh, what? Oh, I must be missing some sort of include. Yeah, people think I'm Canadian. I'll give you Canadian. Oh, yeah, I remember the day when the Edmund Fitzgerald, she shake beneath the waves, and, you know, there a big wave came up, and all the good ship and crew, they did all they could do, but, you know, when the gales of November come, you know, she'd be sinking right under the waves, and, well, this big old wave came up, and she went right down to the bottom of the lake, and, you know, they were gonna, you know, Tim Hortons was gonna sponsor a way to go down there and, you know, pull the boat up, but the boat was sank pretty good. So yeah, I don't think we're gonna be able to get that boat out of there, you know, because never gives up the dead. Oh yeah, it's a tragedy, you know, those poor sailors. But now, you know, they got that song about them, so now everybody knows their sacrifice, don't you know? Hey. Oh, there's got to be something that I'm missing here on the data sheet. You know, I heard about there was some snow in Texas. Like, they got like a 1/4 inch of snow. And all the Texans are like, oh, by golly, I can't believe we got this much snow. But, you know, up here, sometimes I gotta dig tunnels in order to go to the Tim Hortons to get my coffee, you know, because we got so much snow up here. But it's okay because, you know, I got the snow plow and the snow blower, and it's pretty good. Oh, I'm going to go in here and steal some code. You know, stealing's usually kind of wrong, but it's more like I'm borrowing the code. You know, it's like when I borrowed my neighbor's snowblower for 3 years. You know, I brought it back eventually, you know, and then my neighbor's like, oh boy, you know, I was having a hard time, you know, doing my snow because, wait, transmitter enables enable. Okay, so no, it is enabled. What's going on? I turned back into American. Oh, this might hold a clue. The 10 MSBs of the baud register hold the integer part, while the 6 LSBs hold the fractional part. Oh, so that's why they bit shifted it 6 to the left. Oh, okay, that makes sense. All right, here's the generated code, USART 0 baud rate. Let's look at that function. Okay, that's inline define. Let's see, float 20 million divided by 2 times baud rate plus 0.05. Oh. All right, let's just steal their little function there. What did Steve Jobs say? Good artist copy, great artist steal.
I disabled the receive pin and I set it to do a pulse every time it's trying to transmit data. So we can see the pulse. So we know the code is working, but where is our transmitted data? There should be a dip here on line 2.
Oh, because the example's in asynchronous mode. Oh, darn it. So I'm using the wrong example here. Whoops. Okay, let's go back into start. Let's do asynchronous IRQ mode. Asynchronous meaning no clock or no synchronicity. Kind of like atypical, amorphous. Oh, look, there's our new formula. Thank you, Atmel start. Oh, interesting. It's frequency times 64 divided by 16 times baud rate. Okay, well, hey, you know, that's the thing that's cool about Atmel start is you can use it if you're stumped. You can use it to give yourself a hint. Just a little love is all it takes. It'll make the world be better. Blah blah blah.
Hey, it works! Yay! Well, that took long enough. I guess I needed to read my screen.
I'm going to do this. I'm going to take this function and I'm going to put it in a new file specifically for UART. Oh, I suppose I should probably wrap it with something, right? Yeah, so this would be void UART init. And then over here, of course, we need to include that. So include UART H. Come on, there we go. I've been present for the birth of every little creature on this island. Stop saying that! Let's see if it builds. Oh, I see what I did. I don't have the IO or the interrupt functions over there. I could just include those again, or I could make an H file for main and include that. That should, oh, I know I made this. I don't need to be reminded. Okay, there it worked. Yahoo! All right. So what I want to do is I want to make an interrupt-driven transmitter buffer, because you could just sit there and clock out the data and wait for it to all be gone if you had like a string or something, but then your program would come to a grinding halt while you did that. So yeah, let's see if we can make an interrupt for it. All right, let's go ahead and steal the ISR call for the UART data register empty. Looks like it's calling a callback in this program, but I'm going to do mine a little differently because I'm a rebel. Oh no, I'm gonna put my bracket there, and everyone's gonna be like, no. All right, so this will be called when there's no more data in the register, right? So like if once you send the data, you can move on with your life, and then once the output data register is clear, then an ISR will be called. And the reason that's good to do is because the program can continue, and the ISR will only be called when it needs to update the data register with new data if there's some in the buffer. And then according to the data sheet, if you RTFM, we have to clear the register. Well, here's the status register, right? So this is the data register empty interrupt flag right there. And if there's no more data left, then we have to clear that flag. Otherwise, it will continually trigger the interrupt. So that's something to remember. Like sometimes ISR will clear its flag, but sometimes it won't. So again, read the data sheet. Yeah, we can see here in the code configurator, if there are no more elements, basically if the buffer's empty, then see right there, it's disabling the interrupt. Now you're selling it and you're selling it and packaging in it. And so let's see, that would be, you would write something. No, yeah, so we need a way to create a buffer, like let's do a string like hello world, and then we'll need a way to fill the buffer with a command, and then we need a way to dump the buffer over the bus automatically based off interrupts. So let's give it a try. My Snagit capture has been kind of flaky lately with this headphone. I don't know why. I don't know if it's with my headphones or with my computer. Maybe I've plugged just too many things into my USB ports and now they're tainted. Let's do a 16-byte ring buffer. Remember, we only have 128 bytes of RAM. I can do 32. Screw it. Okay, now so let's do a write pointer. So this is where new data will be placed, and then we'll do a TX pointer, and that will be where data is transmitted from, right? So let's just yeah. So like, well, right here. So we can say if, oh, come on, if ring buffer TX pointer, so if there's something in it, then we'll transmit it. Else, we will terminate the interrupt until more data is sent, right? So then what we would do is we'd go back here, and then we just grab this. You couldn't just type it over again? It's like, no. Again, I said I'm being incredibly lazy. Yeah. Be careful, Fry. He's bulging with what might be muscle. I will kick your butt if I wasn't so lazy. But you are lazy, right? Oh, don't get me started. Okay, if ring buffer TX pointer, then export what's in the pointer. And then also in that case, if TX pointer equals 32, basically if we go around the horn and increment it. If that happens, then we reset it, which means you could be in danger of overwriting your own buffer, but that should be all right. So there'll be two pointers. There'll be the data we're writing into the buffer, and then the data we're writing out of the buffer over the UART port. Now, to fill it, let's do void. Let's just call it print. Who cares? Constant char, which means we'll be getting it from flash memory data, or I guess you could call it string. And so let's do this. While the pointer contains something, remember, if you have a string in memory, it will be zero terminated by the compiler. So there'll always be a zero at the end of it. So while that string is not zero, we'll continue to put bytes into the buffer, right? So we will do this. We will take ring buffer, and then it's going to be the write pointer equals current data, and then we'll also just increment it there. And then if write pointer, well, actually let's increment that. Same thing, if right pointer goes around the horn, then we'll put it back to the beginning. So that's just a simple ring buffer.
On the scope, we're getting the first letter H, but nothing past that, so I must be doing something wrong with the interrupt.
Oh, I forgot to do something. I forgot to enable the transmit complete interrupt. There's something else, though. Just filling the buffer isn't enough because you have to actually send a byte of data before the interrupt will happen after the byte of data is sent, which means we need to send at least one byte of data before that interrupt will actually happen. And I just thought of something. If the transmit buffer pointer has caught up to the right pointer, that probably means it's complete as well. So I wonder if we could just say if right pointer equals transmit pointer, then we assume it's the start of a new frame. Actually, no, we should probably wait until the data has been filled first. Yeah, because we wanna fill the buffer and then send the data. So let's just do a local. We'll call it first byte. They do first byte, not me. Oh, I think I found the problem. You have to enable the interrupt right before you send the data instead of doing it down here. That's kind of weird. And then you have to disable the interrupt once you're done sending the data. Yeah, so I've got the pulse running here. And the pulse is happening when the data register empty interrupt is being set. So we actually had to enable that, then send the data, and then look for the ISR to be called. And so there's one for the data register being empty, which is when the data is transferred into the shift register, which actually is what's going out to the bin. And then we could also set up an interrupt after that as well. I think it's finally working. So we have the print function. We grab the first byte, then we increment the data pointer. Then while there's still data, i.e. while it's not terminated by a 0, we fill the buffer, looping around the ring buffer if we need to. Then once that's done, we enable the interrupt. Then we send the first byte. So after the first byte is done being transmitted, it will trigger the interrupt, and it'll say, okay, is there another byte ready for us in the buffer? And if there is, it'll transmit that and also ring around the buffer. If there aren't any more bytes in the buffer, and also we have to clear the byte after we write it. If there aren't any more bytes, we'll do our pulse flag and then we'll disable the interrupt. And you can see it's finally working. There's hello. All right, I struggled a bit with how to make the buffer work automatically with the interrupts. I could have had it like a UART task thing you call every time, but that's kind of dumb and it kind of defeats the purpose of using interrupts. Here's what I did. I got print text, print string, new line, and then UART Send. So basically, you put whatever you want in the buffer, and then once you're ready, you hit UART Send, and it all goes in one package. Easy. All right, let's take a look at the functions. So we have print hex. This can be up to a 32-bit hex. So if it's above FF, then it just prints out 2 bytes. And then we just have a single hex function to print out the 1 byte. Pretty simple. Then we have a decimal. Just uses the modulus division and writes it to the buffer. So basically everything just writes to the buffer now. That way we just have this little routine for everything, including for the ISR. Well, actually ISR has transmit byte, sorry. So once you've done everything that you want to do, you call UART Send. And then, so if there is data at the transmit pointer part of the buffer, then it will transmit the single byte and enable the interrupt, which means all the subsequent bytes in the buffer will be sent automatically by the ISR.
Anyway, there you go. We have 0xFFFF space bottles, carriage return, and line feed. So cool. We have everything we need for debugging now.
Speaking of debugging, if we look at the debug menu here, we see that the CPU has 32 registers. That's really handy because it means it can pass variables to functions without using RAM. However, you have to assume that in an interrupt, it might have to push or pop all 32 of these, which means we have to be careful about how much memory we use. We're using 14% of the RAM and 27% of the flash. So if it's 128 bytes of RAM, 32 registers, we probably don't want to go above like 96 bytes of RAM. That sounds so laughably low. Yeah, because we have to assume like the stack pointer and the registers might be pushed to the top of RAM. That's the thing. The compiler probably wouldn't tell us if we're hitting that. It'll just cause an error later on. I mean, it might. So yeah, I'm going to make sure I don't go past like 75% RAM usage because there's so many registers that might be popped, just to be safe.
For my I2C test, I have a small OLED screen hooked up to it. This should read as device 3C and X. Then I have an FTDI cable so I can read debug information over the UART port, which we've already set up. So let's look at it from a code perspective.
Now, there's a bit of a double-edged sword when it comes to looking for drivers and libraries for chips that might fall within the Arduino range of processors. So the good edge of the sword is that there's usually a lot of documentation and everything is pretty well figured out by the community. But the bad edge of the sword, I don't know if that's the sharp or dull edge, I guess it depends on your perspective, is that a lot of the libraries are made for Arduino. So they'll assume there's Arduino library supporting the libraries. That'll be written in C++, which might not always work. So I was looking around and I found, technobiology, right. And this person has written a tiny driver. I think he's using the 402, but that's close enough. So I actually downloaded, I wasn't able to compile it directly. So yes, this is technobiology, like technobiology. I wasn't able to compile it directly, so I converted it. So David Johnson Davies, technobiology.com. So I'm using this. I left this in the header, so I'm not a complete jerk. So I had to convert it to C from C++, but it's not a big deal. But look how simple this is compared to what Atmel start generated. So I basically converted the H file and the C file, and now I can use it in my program. So what I'm just going to do is I'm just going to scan all the ports and see if there's anything on the I2C port and see if we get a result and print it over the UART. Results 0x3c. That's what it should be. So it looks like, we got a proper acknowledge from the OLED. Cool. Now we can try to put some stuff on the OLED. Time to steal some more code. I mean borrow. SSD 1306. And we're going to go library. Oh man, I cannot type today. Really, the main thing we need is the start initialization sequence. Here we go. Transaction start init sequence. They're putting a bunch of things, or they're putting a bunch of the defines into prog memory, which is how you have to do it with the Arduino. Again, see, this would be unnecessary in AVR Studio, so that's another thing that makes Arduino different. So basically you need to send this startup sequence, but then once you do that, then you can basically just dump raw data onto the little screen. I searched for SSD 1306 init sequence, and I found this GitHub page. So this is it's pretty self-explanatory. I can just rename this function to my own, and it should work. All right, so I grabbed a few different sources online. We have the initialization library. I'm not sure if it's correct. I'll double check it against Adafruit because I trust them a lot more than some rando. Then we have a function for sending a command, which basically is a write command, but you send 0 and then a command instead of just data. And then to send just data, you send 40 hex and then you send a bunch of data. You also have to set the where the data is going to start. I'm just kind of shotgunning this, but let's give it a program and see if it works.
Hey, look, random... Oh, my fingernail's torn up. What a shock. Look, random noise on the screen. I consider that a win. All right, let's dial it in and make it do... I mean, we don't really have enough room for a character set, but that doesn't mean it's not useful. And again, this is mostly to test the I2C library. I don't actually want to use the screen, although you could make like a cool little watch with it.
I RTFM'd a bit more, and I realized that a lot of these commands, it's a command and a parameter, right? So you can't necessarily just send a bunch of data in separate packets. You have to send, let's say you're doing set clock divide ratio and the oscillator frequency, or set multiplexer ratio. You have the command, and then you have the parameter, and they have to be in the same data packet when you send it with OLED send command, right? So basically I have 0, 1 if there's a parameter or not, and then the parameter. And that seems to work. All right, so then back here, we've got OLED set XY. That sets the fine horizontal position and the coarse vertical position. And then we're just going to fill it up with data and watch it go on the screen. Hey, it works! Yahoo! I think it's a testament to the soul-crushing reality that was 2020 that I'd actually written libraries for this about a year ago for my Z80 Note project because that had a I2C screen just like this one, except for it was twice as tall. So I just had to do some personal digital archaeology and dig up some of the routines. But it looks like it works for this one as well.
It's hidden by wires, but I've attached an I2C EEPROM right here. I'm going to see if I can write to it and read back from it. Then I'll know the TWI library is working correctly, so let's look at the code. And we're going to start by RTFM, the data sheet. Read the effing manual data sheet. It's kind of redundant. It's like Sahara Desert.
Okay, write cycle timing. Byte write timing. Slave address, byte address, and then the data. We should be able to send, as long as we keep sending bytes, it should write them sequentially. So you just have to set the starting byte address. Okay, and then how do we read? Read timing, selective. I guess that makes sense. Let's go to the solution. Let's add more files. C file. I'll just call this EEPROM. All right, let's chunk this up a bit. All right, let's make a function called read address. And this is going to be a 16-bit. Okay, let's grab this. Kaboom. Go back over here. All right, so we're going to start up device 50. And how many bytes? Let's just do one at a time, right? And then we're going to tell it what address we want to go to. Now we have to send this as 2 bytes, and it looks like it is big endian. All right, so we'll send the big end of the 16-bit value first. So we'll do that. That'll basically put the top, oh, did I spell address wrong? That'll put the top 8 bits in the lower 8-bit section. And then we'll send the bottom, which will be the value end FF. So we'll do set read address, and that'll set where we want to start reading. Then we could just manually use the read command and then manually stop it. That should work. Include our new function, or our new whatever, our new driver, EEPROM, just like that. All right, blah, blah, blah. So let's just do this once at the beginning. Yeah, let's just steal this. All right, so we'll set read address, and we'll just set it to 0, beginning of memory. It should be all F since this is a brand new EEPROM. Let's get one entire page like that. Then we'll print it in hex. So it should say FF or 255. Oh, apparently there was something on this EEPROM. Either that or I programmed it wrong. Well, let's make some functions so we can write a bunch of sequential bytes like 1 to 255, and then we'll see if that appears when we read it as well. In the case of writing the data, we do it pretty much the same way. We start it, we set the address, but then we don't restart it. We just start writing the data sequentially. I'm just going to write 1 byte at a time, at least for this implementation. And we'll put a delay on each one to give the EEPROM time to settle, because obviously you can't write it as fast as you read it. I switched to a different EEPROM, one made by Microchip. This one is reading as empty. See how those all FFs? Yeah. What I noticed about the other one was a 1 megabit EEPROM, which means it's 128 bytes. But with a 16-bit address bus, that means it actually shows up as 2 different I2C devices. One is the bottom 64K and one is the top 64K. This chip is a little bit more straightforward. Let's see if the write test works on it. I read the data sheet some more. Well, for one thing, write protect is active high, not low. I had it pulled high. It actually has to be low in order for write to be enabled, which makes sense because if it just says WP with no line over the top, that means it's active high. Oops. Also, yeah, so read, we're going to start the device, set the starting address, so 0, 0, 0, 0. Then we're going to restart it and request 128 bytes. Then we're going to put them into an array and a little bit of a delay just for the tiny UART buffer that we have. Let's give it a try. Let's send it. Hey, there we go. So our EEPROM is device 57 hex, and we've read all of the sequential bytes that we wrote, 128. Again, read the data sheet. There's usually a page limit to how many bytes you can read or write at a time. For this EEPROM, it's 128. Yeah, so that worked out pretty well. So cool. We now have a working read-write with the I2C. Now we can move on to bigger and more exciting things. I also noticed sometimes it hangs if you try to read immediately after doing a write. So it does take a little bit of time for the EEPROM to actually write. It's slower to write than it is to read. Remember, that's different than writing to the OLED because those are RAM addresses. So I've got a 50 microsecond delay after each write, and then a 5 millisecond delay after the entire page write, and it seems like it's working pretty well. Cool. All right, I think that's probably long enough for this video. I just wanted to get started with this microcontroller. I think I have a pretty good handle on it. Yeah, pretty neat chip. Combines the AVR core with Microchip peripherals, since Microchip owns Atmel now. Yeah, definitely a lot more powerful than the previous AT-Tinys of the past. I do have a project in mind that will use this microcontroller. Building that's beyond the scope of this video, so keep an eye out for that project in the near future. But yeah, thanks for checking out this video, and I guess we'll see you in the next one.